Good morning, everyone. My name is Steve Burke. I'm an engineering software developer from Datacore's Pipeflow modeling software team. Today's webinar is on our new and enhanced features for faster, smarter transient and pulsation analysis. The purpose of this webinar is to highlight the features that most impact transient analysis in Impulse and xStream and show you how to implement them in your models. There was a previous webinar covering most of the new features in all four products. However, this webinar is meant to dive a bit deeper into the features that impact transient analyses specifically. The workflow of the pulsation frequency analysis modules has been heavily updated, especially for Impulse. So we'll discuss how you can leverage the new PFA features for vibrational analysis and go through the new Impulse PFA workflow step by step. All right, a little about who we are. Datacore has been around for 43 years. We have many software products, including engineering simulation. Our products are sold in over 100 countries with dozens of distributors around the globe. And our engineering simulation products specifically are used in over 400 universities. Here's a look at some of the industries you'll find us in. These include power generation, municipal water, pipelines, manufacturing, food and beverage, and more. This is an overview of our four pipe flow modeling products. They basically break down by whether they are compressible flow or incompressible flow, and whether they are steady state or fast transient. We also have more slow transients with our extended time simulation module, but this is just about fast transients. Today's focus is also on the pulsation frequency analysis module, which we offer for both Impulse and for xStream. So first, let's go over the new features that will impact conventional transient analysis outside of the PFA module. This is one of my favorite new features. It's the parametric steady tool. This allows you to set up sensitivity tests and other tests that require a range of input values in an automated way. So you can think of this as a cousin to our scenario manager that can automatically vary inputs using multiple independent and dependent variables. So there's a lot of flexibility with how you set up a parametric steady, including variable linking and customized distribution of inputs. One model can contain multiple parametric steadies, where previously you might have set up several models with dozens or hundreds of scenarios each for this sort of analysis. As always, the more models that you have to juggle for a given system, the more files that will need to be updated, the greater chance of human error. And more of your optimization and performance visualization work can now be done within our Pipeflow modeling suite. I'm going to show you what that looks like. All right, so this is just modified from our US pump trip with accumulator example. If you want to make the same modifications and follow along there. But basically, if you open analysis setup or click this gear here, we'll be under the new area solution utilities. And I've already created one called max pressure. You would just hit this plus sign to create it. And we have independent variables, the initial gas volume of this gas accumulator. And the dependent variable is the max pressure in pipe 2. So you're always going to have one output per dependent variable per combination of independent variables. So you're not going to have an output for every time step. That's why we're taking the minimum and the maximum of that pressure there. Down in the bottom right, this is where you set up the distribution. So we have it as set to linear, and we're starting at 0.1 cubic feet and stopping at 2 cubic feet with a count of 20. And I've already run this. It required 20 model runs, so I'm not going to rerun it now, but we can click here to open the parametric data results that we already have. All right. And it opens in a new view. Oh, looks like I need to reload the data. All right, here we go. And so we can make a line chart. If you were having, two dependent variables or one independent, you might also want to do a heat map, a contour plot. You can do 3D charts over here, surface charts, scatter charts, even bubble charts where you're showing multiple variables because you're varying the size as well. So you're showing three independent variables. But here we will do the line, just of those two series. So we'll generate that series. So you can see from all the runs that were performed initially as the gas volume is increasing in the gas accumulator, the maximum pressure in that pipe is decreasing. And first it hits diminishing returns and eventually it starts to increase again, possibly due to resonant frequencies or something along those lines. What we're talking about now will impact every impulse model. The sectioning setup in impulse is now fully automatic. This streamlines the model setup for every model, but especially for batch runs. If you make a change in a parent scenario that affects the sectioning, this always cascades to all child scenarios. And previously, this would mean that you would have to finalize the sectioning in each scenario before running the batch, including the parent scenario. That is no longer the case. So this will make batch runs a lot quicker when you're making edits in those upper level scenarios. Pipes can now be manually excluded from impacting sectioning based on the wave speed variance. This is perfect for short pipes that have little impact on the actual timing within the system, but have a significant impact on your sectioning and therefore your runtime. And by avoiding them, by lengthening them, you can avoid the need to artificially lengthen them. So you're not setting all of your pipes to 10 feet. If they're shorter than that, you're just ignoring them from the variance calculation. Manual control is still retained through the customization of sectioning rules. It's still automatic, but you can set the rules for minimum sections, or you can set rules for time step. And this is useful for systems that need more resolution for force analysis, frequency analysis, cavitation, or pipe filling and draining. For most models, this means that the runtime optimization is largely automated. You would use join pipes and junctions tools to identify and streamline areas that have many fittings. And you could then use global pipe edit to flag the shortest pipes to ignore variance. And that's it. That's all the optimization that you need to do now in your model, as you will see later. The transient solver termination can also now be defined in multiple ways. We can do it based on time, as always, but you can also set it based on any transient junction events. So your pump and your valve transients, multi-condition events, etc. Or you can set it based on design alerts. And you can use any design alert you can set up based on the pipe and junction outputs. And this reduces the waiting time because your stopping simulation runs automatically when necessary, or when the data past a certain point wouldn't be meaningful. And if you'd like, you can still continue these halted runs from checkpoints without having to restart them. Let's go take a look at that. Okay, so again, this example is just modified from your existing US ammonia transfer with cavitation that you have in your examples folder. And I've added a graph annotation here, which we won't get into. That was covered in the other webinar. But you can see the maximum pressure along the length of these three pipes, and it peaks here at the inlet to this valve, and it exceeds 600 PSI gauge. So let's say that past that point, there's a chance of maybe the valve rupturing, maybe the pipe rupturing, maybe just the valve leaking. Either way, past this point, you decide that the results aren't meaningful. You can set up a design alert for that pressure and set it to stop when that happens. So if we go over to Tools and open the Design Alert Manager, I have a design alert here, and it's set for all three pipes. And it's when the static pressure on any of them is greater than or equal to 600 PSI gauge. So we'll save that. And if you open analysis setup, now when you go to transient control, you have simulation duration. And there's three options here. You can end it based on time, you can end it based on an event, and you can end it based on a design alert. Here we have it set to this design alert. If there were several, you could pick it from this dropdown. And it has a maximum time of 5 seconds that it'll hit if this doesn't occur. So we can hit OK, and we can run this. Okay, so this time it's not running all the way because it's hit our design alert. And it says the simulation was ended because this design alert was hit at 1.15 seconds. Hit OK. And so now we can view the output, make graphs, do our analysis from here. This is also useful when you don't know how long your system will need to run for something to happen. So maybe you have an event that's triggered by pressure somewhere in the system, and you're not sure if it'll trigger. An event-based transient can be useful in that case as well. But if you decide that you do want to continue running it further, another thing you can do in the analysis menu is you can continue run from checkpoint. So we have this checkpoint that was made automatically. There's always one made at the end. You can customize the checkpoints to have them at some interval when certain conditions are met if you need multiple checkpoints to work off of. But here we have the final one at 1.15 seconds, and we can continue this run to 5 seconds or anything we want to set here. And now we don't need to restart it to go the rest of the way. So if you have a large system with long run times and you want to stop it when something happens in order to save compute time, and you want to continue it later because you decide that what happens after that event is actually important, you can go ahead and do that. You'll notice that we haven't had to adjust sectioning at all. We still have the sectioning panel. That is right here. So right now it's set to automatic, and it has two sections in the controlling pipe. P1, that was determined automatically by variance, but we can also set a fixed count for that pipe or a fixed time step. We can adjust the variance here if you just want to change it that way. And if we had pipes that we could join, we could also click here to join those. And that's really the main optimization step you have now, besides ignoring some of your shorter pipes. We've also improved PCF imports. You can now import multiple PCF files at once, which speeds up your workflows and reduces repetitive steps. We've also improved the file selection method, making it simpler and more intuitive to bring in the files you need. We've improved the import for valves, where we've added the capability to read the valve types for standard valves, check valves, relief valves, and pressure-reducing valves, so you don't need to change their junction type manually after the import. The concentric reducers now convert to area change junctions more reliably and more accurately. And any welded components in the PCF file will now import with zero length connectors connecting them at the welds. We've also added the ability to set pipe length units globally during import. This makes it easier to work consistently across your project. In addition to the usual material linking from the pipe library, you can now define wall thickness and outer diameter by nominal size, which streamlines the material conversion from the imported files. And finally, we added a simple way to flip the upstream and downstream junctions at import, saving time on data cleanup because the pipes are already in the correct direction. And I can show you what that looks like. I'll go over to a new model, click File, then Import Piping Layout from Piping Component File. Okay. Go to the file selection here and select all of the PCF files that you want to import. Again, this time we can now import multiple. I'll click select all to select all the junctions that can be imported. Here you can see that this PCF file was in inches. So we can now change that globally for all pipes to feet. So we're not doing it after the import. Here's the normal link materials view where you could link, all of your 4-inch pipes to 4-inch ANSI steel, whatever you'd like, etc. But if you're dealing with a pipe that's not in our pipe library, you can also just edit the piping specs here manually. And by each nominal size from the PCF file, you can specify the absolute roughness, the outer diameter, and the wall thickness. Edit pipe connections is where you change the direction of the pipes. Looks like here, don't think this one has any pumps or check valves where it would matter. But the thing about PCF files is usually the direction of the pipe is the direction that you drew it in. It may not be the flow direction, which is especially important for pumps and check valves. So if there was some that you needed to switch, you just go through, flip them there. It'll always highlight them. Click it again to flip. That's how we do that. I did not specify any materials, but we can go ahead and import this as if we had. And that's what that new workflow is looking like. This next feature is pipe filling and draining, which is impulse specific, and it models the propagation of gases and liquids throughout your piping network. It's really beyond the scope of the current webinar, but we covered it in our previous webinar, Predict Filling and Draining Transients with Confidence, if you want to check that out. This next feature is also impulse specific. And we've added an option that mirrors the reciprocating compressor functionality that's already in xStream. This enhancement allows us to more accurately model reciprocating pumps. It's especially valuable in the Impulse PFA module because you can use it for steady state pulsation, but it's also included in the base Impulse software. Next, let's go over the features that will impact the, oh, sorry, these are the Impulse and xStream PFA specific features. We've introduced a new force amplitude versus frequency graphs feature in Impulse and xStream, which is part of the PFA module. And this essentially applies fast Fourier transforms to force versus time data. So you can generate pulsation shaking force graphs directly in the software without external processing. And this is something that we've done with pressures for a long time, where we've used it for API 618 and API 674 analysis, but we've now extended this to forces. The forces are defined as usual, so force sets in your existing models are already set up for this analysis. This is PFA, so you're going to be able to identify problematic positive displacement pump RPMs and automate setup of these vibrational scenarios. As always, we can export force information for further analysis in pipe stress simulation software, such as Caesar 2. And this feature makes it easy to visualize force amplitudes across frequencies, identify resonances, evaluate pulsation effects, and streamline reporting for better performance. So this is what the new workflow looks like. We have two essential modes. It really is a three-step workflow. We have the natural frequency evaluation mode. You'll first use this to identify the system's natural acoustic frequencies by applying a pulse to the system and applying resonant peaks. This helps you to pinpoint where the system is most vulnerable to any vibration issues. From there, you can go to the interactive excitation frequencies and pump speeds view. This will be a graph in the frequency domain. And this allows you to highlight peaks to calculate pump speeds that will excite those natural frequencies. It shows the worst case operating speeds that could lead to excessive vibration or fatigue and failure. And it allows you to automatically create the child scenarios to evaluate the RPMs associated with each of those peaks. The last mode is the steady state pulsation mode, and this runs a frequency domain analysis at selected pump speeds. It models pressure pulsations throughout the system under steady state operation, and it enables direct evaluation against API 674 limits and other design criteria. The steady state pulsation mode is actually more flexible than this graphic implies. So the workflow you see here is to automatically build those read-only steady state pulsation scenarios when you have a reciprocating pump. But you can also use steady state pulsation mode independently with or without the prior steps. This allows you to model other types of pumps like gear pumps, custom transients for cyclical pulsation sources, check valve chatter, non-cyclical events if you want, or systems that have multiple pumps or multiple pulsation sources. One thing I did want to note is that the natural frequency evaluation and steady state pulsation mode are both an extreme as well, where they have the same interface and the behavior. But this middle step of the excitation frequencies and pump speeds is not an extreme, and this is due to the impact of choking and temperature on acoustics, which will matter in some edge cases. But in many cases, those same harmonic relationships that you're familiar with will hold true. So I still recommend using the natural frequency evaluation mode as the starting point for finding the reciprocating compressor frequencies of concern and extreme, but you may need to do a broader frequency sweep of frequencies that are near those frequencies. You can check out our recorded webinar, Does Your Compressor Piping Network Comply with API 618? It covers the reciprocating compressor and extreme PFA analysis in more detail, or you can check out the extreme PFA example in our documentation. But here we're just going to go through an example using impulse for pulsation frequency analysis. So we'll be modeling the discharge size of a reciprocating positive displacement pump step by step. There's going to be flow to two systems over at the right here, which are sensitive to vibration, and one of which will be turned off, which we'll be modeling as this dead end. It might be helpful to grab a screenshot of the dimensions shown here on the right before we switch back to impulse. And if you miss anything with the pump setup or you want to work ahead, I'm going to use the same inputs as the pump in the US positive displacement pulsation steady model from your examples folder. All right, so we'll start a new model. I always like to turn the grid on. And to keep it simple, we'll use an assigned flow. But of course, you could also do this as a proper reciprocating pump junction and model both the discharge on the suction side of the pump that way. But for now, we're just looking at the discharge side and doing it as an assigned flow. And we'll continue with the rest of our junctions. So we have bends going over some obstacle here. We'll look at the vibrational forces on these bends to see the stress that's on the mounts there. We'll do a T. Dead end. And finally, the assigned pressure. And I'll double click on the pipes. Just draw pipes along the same path. Now I'm going to highlight everything, right click and auto rotate. It's all facing the right way. Okay. So the assigned flow, we're going to set this to 35.5 GPM. Elevation of 0 feet. Oh, I typed GP. The bends, we'll just global edit. And let's do a bend ratio of 1.5. The elevation at 0 feet for simplicity. I'll apply all of the bend model data and this inlet elevation data. The TE will leave as simple. The elevation will just leave at 0 feet. This will leave at 0 feet for simplicity. And here, let's change it to PSI gauge. Set this to 50. Okay, I believe we were doing 2-inch ANSI steel. This first one will just be 2 feet. And since this one is very short, I'm going to go ahead and go to the optional tab. And this is where that ignore variance option is. So it's going to ignore this when it's setting up the sectioning. It will add a little error to the system timing, but since it's a very short pipe, it's not going to have much impact. It will allow it to have half as many sections per pipe, which will have about a 4x improvement in runtime. So we'll go ahead and set that. The rest of these we will include in the sectioning. We'll keep it at 2 inches, have it 6 feet. Seven feet. 6 feet. 57 feet. These last two will do 25 feet. And 90 feet. All right. And we should be set on the workspace. Let's double check. Oh, they don't have wave speed because we haven't done the fluid yet. Okay. Under impulse standard, we'll just double click on water and set that to 60 degrees. We have to set a simulation duration. You can do time analyses with the PFA module active, and there are reasons you would want to do so with the artificial transient resolution if you have a steady state pulsation source. In this case, we're just looking at the frequency domain, but you still want this to be sufficiently high to provide enough samples for the FFT. There's more information on our documentation site of the factors that affect this, but some of the factors include the communication time of the waves from one end of the system and back. It will need to be higher if you have multiple pulsation sources. For this model, 30 seconds is more than enough. So we use that. Then let's activate PFA if you have it. We're applying it at J1. And we will have it just calculate the cutoff frequency for us. This is going to be 3 pistons, the max speed of 250 RPM, and a speed buffer of 15%. This is just going to go 15% beyond that maximum. And we'll set up the excitation RPM scenarios. So this is the part that is specific to impulse. that will be used to set up the automated scenarios in combination with the graph. We'll set our minimum pump speed here, 125. Looks like these are in feet. Let's change these to inches. We'll do 3 inches, 2.04. 10 inches, 3 heads, 70% clearance. Let's change both of these to PSI gauge. Set this one to 50, this one to 6,000. And we don't need to do anything in the advanced settings. Okay, so it's applied the pulse here at the flow junction. It's going to be twice that steady state flow, and I'll just ping it for a moment. So if we open this, you can see this transient here. Goes from the steady flow and doubles it and back down. Actually, before we run this, we'll set up our forces too. And again, we're worried about the forces that are here on these bends. So we'll set up 3 forces. The first one will start at pipe 2. It'll end at the same pipe. Second one will start at pipe 3, end at pipe 3. We'll do the same for pipe 4 for the last one. Okay, those are all set. Now we'll need to save this before we can run it. Save this as operational analysis. And it looks like everything is defined down here in the bottom right. We can go ahead and hit run. We didn't open the sectioning panel in this case because it was all automated. All right. Looks like we have no warnings here. So let's go to the graph results tab and click the tab here for frequency plots. And we are going to do the outlet of pipe 6, which is where we have a sensitive subsystem that's turned off. That's where that dead end connects. And the outlet of pipe 5, where that T is. Okay. All right. So we can see the more sensitive subsystem here in blue and the T in red. So the lower frequencies are exciting the T more, and the higher frequencies are more severe for this subsystem. And the higher frequencies have more potential for damage. So let's take the 2 higher frequencies that have a large magnitude so we can drag highlight this. We have this 37.5 hertz peak here. So let's right click and say evaluate excitation frequency. So you can see there's harmonic multiples of that frequency at 9, 12, 15, and 18. These are all in intervals of 3 because we have 3 pistons. We'll go ahead and do the same here for this peak at 58.3 hertz. So these are all the child scenarios it's going to generate. We can also add a manual one if there was one that we were particularly interested in, maybe the planned operating speed. But in this case, we'll just click create scenarios based on selected pump speeds. We'll create these scenarios, click yes to continue. All right, we have all of these. So let's go to this middle one, this 187.7 RPM. If we open analysis setup, you'll see now that it's read-only, but it's set up the steady state pulsation scenario automatically with the correct RPM and number of heads. It's evaluating it with API 674, and it's using the cutoff frequency that we specified previously. It's read-only, so the only thing to do is to run it. So this is an artificial transient resolution step that is specific to the steady state pulsation mode. Again, that's why even if we were only interested in the time domain, we would want to run this simulation with PFA on. Okay, we go to the output here, and this time we do have some warnings. So we have some cavitation here in that first pipe. There's a warning here that pipe force calculations are not reliable when cavitation occurs during simulation, and that's because of the forces that are caused when cavitation forms and collapses. We can also see that the maximum peak-to-peak pressure limit for API 674 has been violated at many locations. The pulsation summary can give us more detail about those locations. But since we're looking at 0.4% vapor volume, it's probably not much of concern for our force analysis, but you'll see that it will have some effect. So if we go over to graph results and frequency, let's start with the pressure graph. And again, we're looking at the outlet at pipe 5. The outlet at pipe 6. Generate that. Okay. And here we can see that the limit for API 674 is violated at both of these points. There are 2 frequencies that are violating it at the T, and 3 frequencies, especially this one, at 37.5 hertz, which makes sense since this is the excitation frequency we were worried about, would be damaging our equipment that's connected to pipe 6. Let's make a new graph down here. The vibration will still be under the frequency tab. You'll just click this drop down and hit force sets. We'll be looking at the 3 force sets that we defined earlier. And we can make this logarithmic. This is much noisier than what we were seeing when we were pinging the system. And again, this noise is from the cavitation. We can still pick out the peaks here, and the cavitation was very modest. So it's probably not an issue in this case, but it is something to be aware of, and this is where you would definitely see it. And here we have a peak-to-peak amplitude of 75 pound force. So this is probably enough vibration to be a concern. Certainly combined with what we're seeing with API 674. Uh, if we were instead wanting to set this up for a custom pulsation source, let's say that this was a worm gear, or sorry, a gear pump, we could set this custom steady state pulsation. And here you could have some transient that you're expecting from your system, or you could put this transient on anything, whether it's an assigned pressure. It could also be caused by chattering check valves, etc. But if you want to do it with a transient, maybe you would have some periodic flow with chopped sine wave. Let's keep it at 38 hertz, flow amplitude, 35. Here we would go straight to steady state pulsation, and it's not a reciprocating pump, so we'd click other. It's not going to do API 674 since it's no longer applicable. And we could manually set the cutoff frequency here. And just set that at 200 hertz. Oh yeah, so we would need to know the time steps per cycle. I'm not sure off the top of my head, but you would have to adjust this for the artificial transient resolution. But it would require the average pressure over each cycle to be within some tolerance from block to block or multiple blocks in a row, if desired. And you could tighten those up if you were seeing some artificial transients. But that's essentially how you would set that up. So to recap the results, we identified a problematic RPM that was based on the natural resonance of the system. And the steady state pulsation analysis was performed at that RPM of 187.7, including the vibrational analysis and our API 674 compliance testing. API 674 limits were exceeded significantly at both the sensitive subsystem and at the branch. The vibrational analysis showed peak-to-peak force amplitudes around 80 pound force at this frequency. And the quality of the vibration results were also impacted by the presence of cavitation. So if this was a real analysis, it would be a good time for us to adjust that sectioning resolution. We would certainly want to increase it. We could stand to have higher runtime here. We could also use the unsteady Bernoulli friction model for the transient friction model, or we can use the DGCM cavitation model or some combination of those steps. All of those would clean up some of this noise and make it more realistic. Again, this could be a case where we would maybe also need more samples for the FFT. So we might want to increase that runtime. But overall, this analysis suggests that we should consider pulsation mitigation devices or modifying the operating conditions, the piping design, or the pump selection for this system. So our key takeaways. We covered many of the major new features for transient analysis and how to apply them in your models. You can now run vibrational analysis in the force versus frequency domain. And you're now familiar with the new generation of the Impulse PFA module, which combines the automation of Impulse PFA for rapid reciprocating pump and API 674 modeling with the flexible pulsation modeling that we had in xStream. And that enables you to model more specialized pulsation sources and systems with multiple sources. So these are just some of the new features that are most relevant to transient analysis. There are other interface enhancements in Impulse and xStream that we didn't cover, so be sure to check out all the updates to workspace layers specifically. This year, there were many other features added for all 4 products. You'll see an overview of the new features on the welcome window of each product, with more details available on our documentation website. And for a global overview of these new features, I highly recommend our What's New Key Features in our New Versions Showcase webinar. And for more information on the pipe filling and draining feature specifically, check out our recent Predict Filling and Draining Transients with Confidence webinar. Our website also has a variety of resources if you're seeking more information. This is where you'll find those recorded webinars, or you can find them on our YouTube channel. We can also put you in touch with a sales engineer who can show you our software and get you a trial license. And for existing customers, our support team is always available to address your questions and provide model troubleshooting. And we're happy to help. Just get in touch. And thank you all for joining. Looks like we have time to take some questions. You have any? Let me pull those up. All right, I am not seeing any. Well, thanks again for joining.